Let's talk a little bit more about electric forces and then something we call electric fields and even voltage, which is another term for electric potential. Now, we'll start off simply. Let's say we have a negative charge and a positive charge. What's going to happen to these two charges? Well, they're going to attract each other and pull towards each other. But what if we have two negative charges? If we have two negative charges, they're going to repel and push each other away. Likewise, if you have two positive charges, they will also repel and push each other away. So we know what will happen as pairs of charges are close to each other, but how strong are these forces? You'll recall that the quantity of a charge is measured in units of coulombs. Coulomb, the scientist who's done a lot of work with magnetism, or not magnetism, electricity, derived this equation for us, that the electric force between two charges is proportional to the two charges themselves and is inversely proportional with the distance squared. Then all you have is a proportionality constant. So here in our equation, F is the electric force, Q1 and Q2 are the magnitudes of each charge, and D is the distance between the charges. This letter K is just a constant number that keeps this equation equal. It has a value of 9 times 10 to the 9th Newton meters squared per Coulomb squared. That would be 9 billion newtons meters squared per Coulomb squared. So let's do a quick example here. Let's say that you have two charges. The negative charge is 0.5 coulombs. Should be negative 0.5 coulombs. And the positive charge is positive 0.25 coulombs. And they are a distance of 15 meters apart. Well, we know that the force is just K, Q1, Q2 divided by D squared. So the electric force is going to be K, which we decided was 9 times 10 to the 9th Newton meters squared per Coulomb squared, times Q1, which we said was negative 0.5 coulombs, times Q2, which was a positive 0.25 coulombs, divided by D squared, where the distance is 15 meters. We have to square that. Throw that into your calculator, and you get 5 million newtons. Negative because of this negative, but really, this negative in here means it's an attractive force. They are going to pull each other. They're going to attract towards each other. They're going to move towards each other. If your answer comes out as positive, then that's going to be a repulsive force. They're going to push each other away. Okay, that's electric forces. Now we're going to talk about an electric field. Now, anytime you have two charges close to each other, there's going to be a force on each other. In other words, they're going to influence each other. Now, the electric field starts to include the location of these different charges. Basically, instead of talking about the interaction between two very specific charges, we're only looking at one charge and looking at the field of influence due to that one electric charge. Put it another way, if you put a small positive charge near another charge, what would happen? Well, if you put a positive charge somewhere close to another positive charge, they would repel. And so you end up with a series of lines pointing away from the positive charge because any small positive charge would be pushed away. Whereas If you have a negative charge and you put in a positive charge there next to it, it will be attracted. And so anytime you put a small positive charge near the negative charge, no matter where it is, it will pull it in towards the center of the negative charge. Okay, so those are the most basic electric fields or fields of influence due to positive and negative charges. But it can be more complex. We could say, well, what if you have a positive and a negative charge close together? Well, it'll start off near the positive. Any small positive charge would be pushed away, but as it got further away, it would actually start being attracted by the negative charge. And so you end up with this weird curved pattern that you see in this figure. Patterns can get a little crazier too. What if you have two positive charges? Well, let's say that we have a positive charge somewhere around here. It's going to be pushed away by the positive charge on the left, and pushed away by the positive charge on the right, and it just gets pushed away upwards. So basically what we're doing is we're taking these fields of influence from each charge and adding those fields together, and it gives us these different patterns that you see here. Now, voltage is very much related to these electric fields. Voltage, the way we calculate voltage is the amount of potential energy per unit charge. In other words, the voltage is going to equal the work done divided by the charge to which it's done. So let's take these two charges, both of which are positive 1 coulomb each, and let's take the one on the right and let's push it towards the one on the left. Now they're going to be repelling each other, so you have to do a certain amount of work to move that charge. The amount of work done to move that charge divided by the charge itself, 1 coulomb, that would be the voltage. We measure voltage in what's called the volt. 1 volt is equal to 1 joule, which is the unit of work, divided by 1 coulomb, the unit of charge.